Thank you. Thank you for the introduction. So yes, I'm Filip Sośnicki. I'm a PhD student at the University of Warsaw, supervised by Dr. Michał Karpiński and Professor Czesław Plazewicz. So today I would like to show you my results I obtained during my 4 years of PhD studies at the University of Warsaw on the subject of electro-optic shaping of single photon pulses. So let's start with short motivation. So I think one of the main goals of opticians is to be able to control light and to use it for different applications. So by controlling the light, we mean to be able to control in the chosen degree of freedom of light. So here I show you three main groups of degrees of freedom. So the first one is polarization, of course, where the control is quite straightforward. We just use some wave plates or we bend fiber, and so we achieve this way the change of polarization state of light. Then we have spatial mode, and by spatial I mean any spatial mode. So this can be either path or a spatial mode, or even spatial mode with optical angular momentum. So it's funny donut shape beams. So here modulation, of course, path is quite straightforward. However, in the spatial mode, especially optical angular momentum, it starts to be a bit of technical challenge. However, this has been done. We can control light, classical or quantum, in the spatial mode, in the spatial degree of freedom. But it's still technically challenging. And then we have spectral-temporal degree of freedom, where by this I mean either temporal modes or time of arrival of single photons, or time between arrival of photons from photon pair, or of course we have spectrum. So in this regime, actually in classical optics, we have already quite good control, and the proof for this is that all the telecommunication in the fiber network, right, the existing fiber network, commercial one, is actually using this degree of freedom. However, many of these devices are actually using amplifiers and filters. So this means that in the quantum regime, we still needs to develop some methods to be able to control light. So what we can get from such spectral-temporal shaping, so from control of time frequency domain, is of course we can either use this degree of freedom for coding quantum information. So for example, we can assign different symbols to different wavelengths to use frequency binning, or we can assign different symbols to different temporal modes and then perform quantum computation or quantum key distribution. But this is not the only possibility. We can gain as well using different degrees of freedom for any coding and other stuff. But we still have to care about spectrum, and this is because when we, for example, want to use different quantum devices, such as, for example, spontaneous parametric down conversion source and atomic ensemble working as a quantum repeater, we still have to care about spectral match of these two devices. So, for example, if we generate photons by SPDC, these photons are quite broadband, and then if we try to couple them in the atomic ensemble, which line width is quite narrow, the absorption line width is quite narrow, then we'll have a large spectral mismatch, so the efficiency of this connection will be very low, and it will work effectively as a filter, which we don't want here. So, so what we can do is to put some interface in between, which will be able to either shape our spectrum or compress it such that the total intensity of spectrum will be constant. So still we can gain some even if we don't use this direct in the quantum computation. So from theoretical point of view, what we have is our wave function of let's say single photon, which we can give in either in the spectral domain or temporal. And here we are working in the slowly varying envelope approximation, where tau is the time in the reference frame moving with the center of the pulse. So always center of the pulse is 0 time. And we have spectral and temporal mode, which are of course connected by a Fourier transform. So the Fourier transform of the temporal mode is the spectral mode. So what we actually want to do is to take a single photon with once described by one mode, and then transform it by some transformation to a different mode without changing its quantum state. So we preserve our quantumness. However, so we need to have this operation unitary. So by unitary, we can use only operations that are phase only. So in the spectral-temporal domain, we have either spectral phase or temporal phase. And of course, using only spectral, only temporal, we want to do much with it. So then what you can do is to chain these operations. So you apply one after the other, and by this you obtain much more general transformation. Okay, so this is what we want to do. So how we apply these phases? Let's start with spectral phase. So what we can do, of course, constant phase is trivial. We don't care about constant phase. Here, linear phase is also trivial, since this is just delaying the pulses. Then we have quadratic phases, very important. This is chromatic dispersion or group delay, group velocity dispersion. So what we can see always in ultrafast textbooks is like gratings or prism-based compressor stretcher or other Forest line, which is usually based in free space. It applies relatively small dispersion, but it's tolerant for high power, and we don't need either of these. We need to be able to apply high dispersion, preferably within fiber, so it will be compatible for the existing fiber network. And then we work with single photons, so we don't need this high power tolerance. So instead, we have different devices, which is much simpler, I think. And this is, for example, optical fiber, where we have dispersion, chromatic dispersion at 1550, in one of the most popular fibers, which is SMF28. We have 18 picoseconds per nanometer per kilometer of dispersion, which is connected with some loss. So if we want to have a given amount of dispersion, we just cut the fiber, connectorize it, or splice it, and then we have our dispersion device. Of course, when we need a very large amount of dispersion, that means that we introduce a large amount. We need a long fiber. It introduces a large amount of loss, and it introduces latency. So we have to wait for our photon to be processed, let's say, by the optical fiber. So, but in general, optical fiber is super tool for to be used up to, let's say, 10 to 20 kilometers. But if you want more dispersion, we can move to chirp fiber Bragg ratings. This is like a piece of fiber, like 1 to 10 meters of fiber, which has inscribed structure, periodical structure with periods changing linearly, and it works effectively as a mirror, which reflects different wavelengths at different phases. So this whole device works in reflection. So you put additional circulator in before to have input and output port, and the whole module looks like this. It's even smaller than a spool of fiber of input-output connectors. And this whole device gives, including circulator, gives us 3 dB of loss, which seems to be much higher than 0.18. But here we have we have up to 10 nanoseconds per nanometer of dispersion, which is equivalent of more than 500 kilometers of this fiber. And with this loss, we'll have like 90 dB of loss. So we have to use chip fiber gradings in this regime. Of course, it has a low latency because it's quite short fiber. And after all, it has also possibility for arbitrary spectral phase. So we can instead inscribing linear changing period to have some other structure to apply different phase. But here I will focus only on the quadratic phase, so the linearly changing period. Okay, so this is spectral phase. Now you want to move to temporal phase. So what we can do is to use optical nonlinearities, so like processes like some frequency generation, pro mixing, etc. So these are probabilistic processes, which so not every single photon is promodulated, only with some probability, and it can be quite noisy because we need additional optical pumping, and usually quite complicated because we need some additional optical pumping as well. Of course, these are also limited by the phase matching, so we don't want to use this. We use instead direct electro-optic phase modulation. So here you have how the electro-optic phase modulator looks beneath the casing. So we have, this is wave-guided. So we have here some substrate lithium niobate, which has a waveguide in it, and 2 electrodes, which is ground and signal electrode. And this works that we put our optical signal through the waveguide. We put our electric signal to the signal electrode. Then these two propagate together. The group velocities are matched. So and by electro-optic coefficient, we imprint phase which is proportional to the applied voltage on the optical pulse. So such electro-optic modulator has some important parameters. Of course, the first one is the half-wave voltage. So the voltage for which we have a pi shift in phase on the optical pulse. We have very important is loss, which is 3 dB when we have already connectorized it with fiber. So fiber pictate electro-optic modulator. Then we have bandwidth, since all electronics have its maximal frequency that can work with. And here we can go to 10 or 40 gigahertz. And then there are two parameters that are nowhere shown, but I think are also important, which are breakdown voltage. So the maximal voltage you can apply to the modulator. So this is the voltage when you start the electrodes start sparking to each other, and maximal power threshold. So you just apply a large electric power to it. Of course, the same applies for optical as well. And you just heat up the whole electro-optic modulator, and bad things happens to it. So there's some limitations, and these you won't find in any data sheet, because to measure them you have to actually break the modulator. So it's kind of hard to do this. Okay, so we have phase operation. So what we can do with this? So to explain this, I would like to show you the optical spacetime duality. So this is a framework which arises from mathematical equivalence of equations governing parallel diffraction and narrowband dispersion. So here we have equation of, for parallel diffraction. We have our derivative over propagation. Then E is the spatial envelopes, spatial envelope we have. X is the variable over this function works. And then we have this imaginary factor, imaginary constant, and the second derivative over x, and again the envelope. And then when we look into narrowband dispersion, we see exactly the same structure. So again, derivative over propagation, then envelope as the slowly varying envelope in time, where tau, I remind that this is time moving in the reference moving with the center of the pulse. So zero is always in the center of the pulse. Then you have again this imaginary factor constant, and second derivative of our parameter, which is time here, and envelope as well. So mathematically, these two equations are exactly the same. We only changed some letters and some parameters. Okay, so let's explain it using some figures. So here we have paraxial diffraction. So we start with some beam with which is quite narrow and spatial. However, it has some wide distribution of angular frequencies, and this width of angular frequencies we see as a curvature of wavefronts. So because these are pretty curved, we see very quickly that this beam is very quickly diffracting. So after this, some propagation, we have much broader beam. So the same happens in the in time. So we have some dispersive elements, or for example, optical fiber, which introduces group delay dispersion. We start with very short pulse, but it means that it has to be quite broadband in spectrum. And then we propagate it for this dispersive element, and what we see that the spectrum is the same, but the pulse is cheap, so it's just longer. Okay, so this is one case. So let's go to the a bit different one. So for example, using this optical spacetime duality, you can explain this as well. In this case as well, so we have like two beams. With one is paraxial, very low diffracting, so it has very narrow angular frequency distribution. And the second is the same, but it's deviated by some angle. And this means that in the angular frequency, it's shifted towards one of the sides. So in spatial, they first cover each other, but angular frequencies, they're shifted. So after some propagation, the spectrum, of course, doesn't change. However, in spatial, they start to separate. The same we'll see in time. So you have two pulses, which are highly synchronized at first. but their spectra, they have different colors. Then we propagate through the, let's say, optical fiber, and then spectrum again is the same. However, they start to separate in time. And this is methods to be used, for example, for time of flight spectrometry or dispersive spectrometry, when we map our spectrum into time domain, and then we use temporary result detection, so we can measure actually spectrum in time. Okay, so this is one case. So how to actually make this deviate this beam by some angle. So what we can do is to put into a beam a prism or a wedge, so something that imprints a linearly changing phase across the beam. So what happens here is that this wedge or prism introduces a shift in angular frequencies. So what happens after some propagation is that again the spatial distribution shifts. The same we will have in temporal domain again, where we start with some pulse, with some spectrum. We apply a linear phase in time. So it means that we apply to our electro-optic phase modulator a linearly changing voltage in time. And by this, we achieve shift of the whole spectrum. So this is the way how to make the spectral shift I showed you before in interface. So this is one device we can set up. The other one is of course a lens. So how does it work? So here we have some setup, spatial setup to change width of the so some collimating setup, so to change width of the propagating beam. So here we first start with very quite wide in angular frequencies, but narrow in spatial beam. Then we propagate it diffractively, and we have again spectrum is the same, but the spatial is broader. And then we apply lens, which applies a quadratic phase in spatial in x, so x squared. And then what we achieve is that we change the curvature of the wavefronts, which means that we change the width of angular frequencies while the spatial mode stays the same. So the same we can do in time. There we have again short pulses and broad spectrum. We propagate it through the dispersive media, and the pulse in time will get broader. And then we apply a quadratic phase, which is so quadratic phase in time, which is synchronized with our pulses in time, such that 0 is at 0. And then what we achieve is that the pulse will not change in the electro-optic modulator, so it will be broad again, but the spectrum will be much narrower. So this is scheme for compression, for example, of single photons. All right, so here we have methods. So let's go to some first setups. So first I will base on work done by Michał Karpiński in Oxford, which they show spectral shift of single photons. They use as the pulse laser, some photon burst source, then separate both photons and modulate at least one of them with an electro-optic phase modulator driven by an amplified signal from RF signal waveform generator, so a single, which generates a single tone signal, so a sine wave of some frequency. Of course, it has to be synchronized with some photodiode and phase log loop, but I will tell you about this later. And then just they measure a single photon spectrum. So what they show is that here you have spectrum of the photons, which is the black one, and the red and blue ones are shifted by using negative or positive slope of the sine signal. So we can observe more than half a nanometer shift both ways. And to prove it that this whole methods are good for quantum regime, they show Hong-Mandel dip, where they show that when you have unshifted photons, they are really good match spectrally matched, so you have good visibility. Then you shift one of them, so they start to separate in spectrum. So you start losing your the visibility of the Hungry-Mandel dip, and then when you shift the second one as well, you will see that the visibility is restored. So that proves that that's quite good for in the quantum regime. So building our electro-optic time lancing platform in Warsaw, I started with very simple setup, which consists of pulse laser, some filtering, electro-optic phase modulator. So here we modulate our pulses generated by pulse laser and measure it by optical spectrum analyzer, while the modulator is driven by an amplified signal from photodiode. For high bandwidth photodiode, the one more thing to be added here has to be the delay line. And by adjusting the delay line, we can synchronize our optical pulses modulator with either of the slopes of the pulses from photodiode. So here are the results. Here we have the spectrum. The blue one is the spectrum of unshifted photon, not shifted photon, optical pulses, while the orange and the green one are shifted with positive or negative slopes. So you can see that this starts to be unsymmetric. However, you can achieve more than 1 nanometer of shift one way, so in total 2 nanometers. And this asymmetric property is coming from that we're using a pulse from photodiode, which is not a sine signal. So here we have a bit faster slope. Here we have slower slope. So this is the phase profile we use from the measured from the photodiode. So this is the phase profile. So one of the slopes is faster than the other, and the others as well a bit shorter. So that's why we have a smaller shift towards one of the waves. Okay, so because we didn't have yet actually Mach-Zehnder interferometer yet set up, I was looking for a way to measure the phase profile without the Mach-Zehnder interferometer. So what we can do, we can check that our spectral shift actually is proportional to the slope, so to the derivative of the phase profile. So we can derive the phase profile from this spectral shift by this way. So we have to first measure our spectral shift with dependency of the synchronization. So this is what we done. So this is the spectral shift with already some subtracted constant to start at 0. So we can see how the pulse shifts either way the spectrum. And then what we do, we integrate it from 0 to some time of interest. And by this, we can retrieve our phase profile. You can see this is the measured phase profile with this method. And you can see that it's almost the same as the one from Mach-Zehnder interferometer. Of course, there are small differences, but the general shape looks pretty the same. So that's quite fun. Then we can go to temporal lensing. So this was using a time prism or time wedge, so the linear phase. Now we want to use the quadratic phase. So normally, what we would do is to again, let's say we want to spectrally compress single photons. You have pulse laser, then you produce photon pairs. These pairs are separated, so photons from the single pairs are separated from the PBS. One of them is heralding. We use, the second one is chirped in a single mode fiber. It goes through electro-optic phase modulator, which is modulated with the quadratic phase in time. And then it's measured in the time of flight spectrometer. So this is the method I told you before, where we first chirp our photon, and then we use temporally resolved detection, and hence obtain a spectrum of single photon. So here we need to drive it with quadratic phase in time. So what we can use is the amplified signal, generate a single tone signal, so a sine but this time we can synchronize to maximas or minimas, so any extremas with the correct sign we use to obtain a quadratic phase in time. But there are some problems with this setup. So first of all, we need to have we are still delivering power towards electro-optic modulator and amplifier, which limits the maximal power. So this is the maximal power threshold I told you before. So we cannot use too much power because we just simply burned all the setup. So this is like a limiting factor here, and it's even worse because we have a phase lock loop, which everyone who works with RF knows that phase lock loops are usually complicated. Some phase don't want to work, and they can introduce phase noise. So this is some disadvantage of this method. So instead, what we did in our lab was again use a photodiode. So this part of the setup is the same, but what we changed is the driving part, where we use again delayed optical pulses, which generate pulses, electronic pulses via photodiode, high bandwidth photodiode, which are then amplified, and they modulate our single photon. The only thing we have to do is to adjust the delay such that single photons will be synchronized with minimas or maximas of our pulses. And this synchronization is natural because the pulses are synchronized, so are generated directly from optical pulses. So that's very nice. And what we achieve with this method, that here you have a spectra of single photons, of the modulated single photons, measured single photons. So you have the orange one is the reference spectrum, so the input spectrum. It has about maximum of about 600 counts per second, sorry, per hour in the maximum. While here, the green one is the compressed spectrum. So we see about 12 compression, 12-fold compression. So we see here an increase, so enhancement. I would call the ratio between maximal intensity of the compressed versus the input. So enhancement here will be about 10 or 11. We see some enhancement in this part of spectrum, and it was proven that this is a very stable method because we ran the experiment for 24 hours, and we saw that the drift here was up to 100 picometers, which was very slow, and you can actually see that this is it was measured during night, then in day, and at night again, and so this drifting is caused by environmental process, for example, temperature or pressure. So it has been proven to be pretty stable. So we're very happy about this. We did a few more things because it's we now not using a sinusoidal but a photodiode. It gives us additional advantage that we can use it for modulating different let's say photon traces, let's say trains. So what we can do is take our pulse laser, and now by use of interferometer with adjustable arm, we can generate this double pulses, like this train of, we call it aperiodic train of pulses, because while the period of the laser is 12.5 nanosecond, the delay between the two pulses we can adjust to have the ratio of the delay to period is not non-dividable. So by this, we use this train of optical pulses to be modulated and to generate our pulses to be modulated, to modulate them. So what we see here, then if we properly synchronize them, we see again the orange one is the input spectrum, the blue one's again compressed spectrum when we have time lengthening for both pulses, and the dashed green and red curves are when they are so synchronized such that only one of pulses is modulated. So only one parabola is correctly synchronized. So what we can see is we look at enhancement, so this ratio of the output, the compressed spectrum versus the input spectrum. So our time length behaves constantly the same, more or less, of enhancement about 10. While if we use the sinusoidal singleton, I think this was 10 gigahertz signal, you will see only that for only particular delays, it will work well, but other ways, it will only modulate single pulse. So that's what we call it an periodic time length, which works really well. Okay, but what if we want to go? So here we had like compression, 10-fold compression more or less, enhancement of 10. So how we can go to higher compressions? So we, for example, you want to couple this SPDC with so photons generated by SPDC process into atomic quantum memory, for example, where we have line width of 100 megahertz. We would like to need many orders of magnitude compression. So it means that if we target this 100 of megahertz bandwidth, we need a very long this parabolic region, about of 10 seconds. So that's already hard because then we have sine, which is very slow. So it means that we need to increase its amplitude. However, here we are, as I said before, limited by the maximal amplitude we can use to not simply burn the modulator. So instead of using the sine signal, so the approximation of the any extremum, we can use a concept of time, of Fresnel length. So we use parabolic modulo 2pi function, and this is inspired by lenses existing as well in the spatial domain, which are Fresnel lenses employed usually in lighthouses or some lamps, which are well, just very big lenses that can collimate beam very well to have a very large beam, while the focal length is quite slow, small. Okay, but here the challenge lies in generating such signals, for generating such electronic signals, because all the electronics has its frequency response. So, well, first we have to use an arbitrary waveform generator instead of any generator. So the generator that is able to generate any signal given in digital form, and all the electronics are characterized with frequency response. So it means that this electronics generates different frequencies with different amplitudes. I mean, it's not able to generate, let's say, 10 gigahertz sine at the same way as 5 gigahertz. So it always has some drop of the frequency response. So what we need to do, so we want to generate such signal, such electronic signal. And what we see here already is that, especially when you have that, low resolution screen, is that the frequency here is increasing very quickly. And if you have this low resolution screen, you will see just blue blob here because it's high bandwidth, high frequency. So first we need, so we're going like almost linearly with frequency on both sides. And so this is the first effect. The other one is that we need to generate quite well this modulo points. And this is very challenging because to properly generate them, we would need infinite frequency, which is impossible, of course, in the realistic world. So we have to work somehow with this. So all of these are measured signals with very high bandwidth oscilloscope. So when we use arbitrary waveform generator, we start generating such waveforms. We see two effects here. So first one is that amplitude of this is more or less linearly decreasing both ways. So it comes directly from the magnitude of frequency response, that higher frequencies are harder to generate. than the slower ones. And the second effect, we see that the whole thing is a bit crooked towards one side, like a bit rotated. And this comes from the phase of frequency response. And this is the phase of frequency response tells us that one frequency can be generated a bit after the other one. So, for example, between let's say 10 gigahertz and 5 gigahertz frequency, we can have like few femtoseconds shift, and then we'll see this asymmetrical, this asymmetric thing. And it gets even worse when we try to amplify it, because amplifying it with high bandwidth is even harder than generating the signals. So you can see that we have some parabola in the middle, but all of these these modulo points are almost gone. So what we can do, we can most often used technique is to use precompensation. So what we do, we take our signal, idea signal, before generation, we multiply its spectrum with the inverse of frequency response. So we actually amplify, artificially amplify these high frequencies. And then what we get then we generate this and put it for amplifier. And what we obtain is much better looking signal. We can see that maybe this Fresnel should work. This Fresnel signal should work. So first, this is the setup we used. So we have again pulse laser, photon per generation. As before, we split the photon pairs on the fiber polarizing beam splitter. One is going for heralding. Again, we use time-of-flight spectrometry. And the only change here is that instead of optical fiber, here we use chip-fiber drag rating, since we need a large amount of dispersion and a high bandwidth electro-optic phase modulator, which is driven by high bandwidth amplifier, which is amplifying signal from high bandwidth arbitrary waveform generator, where we generate this Fresnel-like waveforms. Of course, it needs some signal for synchronization. So we use photodiodes for this. And first we made some classical light experiments to see how well it works. So we used a very high resolution optical spectrum analyzer with resolution of 20 megahertz. And here you can see the measured spectrum. So the input one is just this line, the orange line, which has width of more or less 0.9 nanometers, and we were able to compress it down to about 3 picometers. So it's almost 400 megahertz. So it's like in width, it's about 270-fold compression. So we have compression by more than two orders of magnitude, while the intensity, the enhancement, so the increase in density is over 90-fold. I developed during my master studies some simulation to simulate such Fresnel lenses, and it seems that we know what we are doing, since the simulation shows very close results. So this is the one compression, but to fully show that actually this Fresnel thing works, I performed a test where I used a different duration of the Fresnel waveforms. So I started generating only the parabola. Then I was adding more and more wrapping points up to full waveform you saw before. So the spectrum I showed you is here. So here we have enhancement. So this is this ratio of the maximum intensity after the compression and before. And what we see here is that we have more or less linear enhancement, increasing enhancement in terms of this duration of the Fresnel waveform up to some point. And this point is given by bandwidth of our electronics. So here to generate even higher, even longer waveforms, we need much more frequency range. But we can see that the Fresnel thing is working. quite well. So we performed some tests with quantum light with the setup I showed you just before. So these are preliminary, and we know already that we are below resolution here. But what we observed during 1 hour of acquisition was compression down to 1.5 or less 1.5 gigahertz of bandwidth of 1.5 gigahertz. So during 1 hour, so it seems to be pretty stable. The enhancement here, so the ratio is about 12 or 15. So it's not as good as the previously shown 90, but here we know that are for sure below the resolution of our time flight spectrometry. And since this test, we already learned how to generate the Fresnel waveforms better. So we have still some room to improve. Okay, so let's conclude quickly. So what I showed you is that we can use electro-optic phase modulation for either shifting spectrum of single photons or for compressing it either by different orders of magnitude. So either by 10 or more than 200 using a different chip fiber drag ratings. I mean, availability to use different modules would allow us to use even different magnitudes even different factors of compression factors. So I showed you that it works both with classical light and with quantum light, that we have a very well working already electro-optic time-lensing platform, and we expect even more results soon. So thank you for your attention.
Okay, thank you very much for your very nice talk.